Good afternoon, everyone. Welcome to the Endlinger Center for Energy and the Environment Highlight Seminar. My name is Sujit Dada. I'll be hosting today's seminar speaker. First, I just want to remind everyone to feel free to post questions in our Q&A window, and then Professor Osuji will answer them after the conclusion of the presentation. And we'll get started. It is my absolute pleasure to introduce Professor Chinedum Osuji from the University of Pennsylvania for today's highlight seminar. Chinedum received his undergraduate degree in material science and engineering from Cornell, and then his PhD in materials and science and engineering from MIT, where he worked with Ned Thomas on studies of structure, property relationships, and self-assembly of liquid crystalline block polymers. And then he was a senior scientist at Service Logics Incorporated, where he worked on soft lithography. And then he was a postdoc in applied physics at Harvard University with Professor Dave Waits, where he studied shear-induced structure and dynamics of colloidal gels. And then he joined the faculty at Yale University in chemical and environmental engineering, where he rose through the ranks and joined the University of Pennsylvania in 2018, where he is currently the Eduardo Glant Presidential Professor in Chemical and Biomolecular Engineering, as well as serving as an associate editor for the journal Macromolecules. Professor Osuji's group focuses on the structure and dynamics of soft materials and complex fluids in many different ways. And he's been recognized for his research over the years with numerous awards. For example, he's a fellow of the American Physical Society. He received the NSF Career Award, the ONR Young Investigator Award. More recently, he received the Dillon Medal of the American Physical Society and the Nano Research Young Investigator Award. On a personal note, it's been a great pleasure for me to know and be inspired by Chinedum for many years. In fact, he recently reminded me that when I was an undergraduate many years ago, I reached out to him for advice on where to go and what to do for graduate school. And over the years, I've been inspired by Chinedum's work and continue to be inspired by his work, which I think particularly uses deep fundamental science to address important engineering problems relating to energy and the environment. And today's seminar is an example of this. So without further ado, I'll turn the floor over to Chinedum. Chinedum, it's an honor to have you here. Thank you.
Thank you, Sujit, for the very kind introduction and as well for your hospitality on this virtual visit. Thank you also to the Endlinger Center and those of you who are out there listening to this webinar. I will share my screen now and hopefully not encounter any difficulties in so doing. And now I should ask the customary, can everybody see my slides? I hope so.
You can.
Okay, excellent. Okay, so I'll start. So today's presentation is really about our work on nanostructured materials for membrane applications. And as many of you out there know, or might learn today, membranes have a lot to offer when it comes to the water, energy, and food nexus in terms of their ability to reduce the energy intensity of many chemical process operations. So my discussion is going to start. I don't want to numb you with statistics. I think many of us are well informed about these things nowadays, but the issue of water scarcity is a real one, right? And so on the left here is a chart readily accessible that looks at the number of people that are affected by water scarcity, essentially, over the last 120 odd years, right? And we can see here that global water consumption basically is going up rapidly across the world, and it's going up at a rate that exceeds the rate of our population growth. And on some level, that's to be expected. What it tells us is that we're consuming more and more water as we have more and more people, but we're doing so at a rate that's exceeding the rate at which people are being added to the population. So efficiencies that we're harnessing in terms of water usage are not yet great enough to offset the increased demand for water that comes from higher standards of living. Water stress is a real thing. I can't say as yet that this is a problem that's near and dear to my heart, but I grew up in Trinidad and Tobago, a small island in the Caribbean just off the coast of Venezuela here. And I can tell you already that when I was a younger version of myself growing up, we had water issues. We would have periods of, during the year during which we could not get large amounts of water, and we had to rely on tanks. And since I've left Trinidad, every time I go back, right, in the 20 years or so since I've left Trinidad, the weather certainly is warmer. I feel it, others feel it as well. And periods of drought during which you have to rely on tank supplies or truck supplies of water are longer now than they once were, right? And so Trinidad certainly is not in a dire situation in terms of water scarcity, but water scarcity is a real thing, and it impacts far too many people around the world. And it's only expected to get worse in the coming 20 or 30 years. Okay, there is unfortunately a plethora of sites where you can go to read about water scarcity, and it's a bit of a morbid situation, but you can go, for example, to this site, worldwater.io, which has a real-time clock that shows the number of people that's affected by water scarcity worldwide, right? And so this number right now is about 2.4 billion people, and of course that number is rising, right, every day, every minute, every second, if you believe, of course, this counter. But the point is that water scarcity is a real thing, and it has severe implications for humanity going forward. Again, so not to belabor the point or to numb you with statistics, there are real positive impacts to be had, of course, as you might expect, from providing plentiful clean water to people. And I've just highlighted a couple of pertinent issues here, right? So how does providing clean water solve economic issues? Well, certainly it does. Every $1 spent on adding access to water and sanitation systems generates, multiples of that in costs avoided and productivity gained, right? There are also gender issues wrapped up in clean water supply, and you can see this a lot in the developing world, particularly in sub-Saharan Africa. There are also issues regarding world stability, strategic issues pertaining to the availability of water supplies that are becoming more and more pernicious as climate change becomes more and more apparent. Okay, so water scarcity is a real problem, and we have to take action to address it. Of course, energy and water are indelibly linked, and as this chart from the International Energy Association shows, the amount of energy that's consumed in the water sector has been rising steadily over the past many years, and it's projected to continue to rise. And we spend quite a lot of energy on water processing, right? Both on the supply, distribution, wastewater treatment, transfer, etc. So for example, in the Middle East, where desalination is hugely important, is strategically important as a method for water purification, the Middle East is projected to go from 5% of their energy utilization to 15% on desalination by 2040. Okay, so there are serious implications in terms of energy utilization that come from the need to procure, distribute, and treat water. So the energy water nexus, I think, is pretty well established. There's a lot of awareness in the United States, and I think in chemical engineering communities and in physical science and engineering communities more broadly, regarding the fact that energy and water intersect in very meaningful ways. And again, presentations such as this can get bogged down in the statistics, but the statistics paint a very important picture. A lot of energy production, so 3 to 4% of US electricity production, is directed towards water supply and wastewater treatment. And conversely, the energy industry uses massive amounts of water themselves, which oftentimes needs to be treated before it can be released back into the environment. Okay, 45% of all water withdrawals in the United States are for thermoelectric cooling associated with power generation, for example. Okay, so these two issues are indelibly linked. And of course, it's not difficult to understand how food or land usage also figures into that calculation, right? So agriculture is a major consumer of water. People need food to survive. And the water that's used for agriculture oftentimes should be treated, if it's not being treated, before it's allowed back into the environment. So the point is that you get runoff waters from agricultural production, you get uptake of pesticides, contaminants of emerging concern, and so on, that originate from agriculture that directly impact then the quality of surface waters and directly impact how we need to treat waters before they can be used for other purposes, whether drinking or otherwise. So these issues are all strongly linked one to another, and they're being exacerbated, of course, by climate change. So these are dire issues that need to be attended to. So what are the options? What are the opportunities out there for us, right? So in a world in which we're facing dramatic shortages of water and larger segments of the global population are facing water scarcity, we need to look to alternative sources of water, both for human consumption as well as for agricultural use or industrial use. And there are alternative sources of water out there. So for example, brackish water is a potential source of potable and non-potable water. Agricultural drainage, municipal wastewaters, and so on are all important sources of water, but they're also important sources of materials and resources that can be recovered from those wastewaters and put to use. So I've taken two plots here from a paper by Benny Freeman last year in ACS Macro Letters that highlight the potential for resource recovery, for example, from produced waters or municipal wastewater, whether you're looking for nitrogen and phosphorus-rich wastewater streams, or from produced waters or runoffs from mines, for example, if you're looking to recover metal species, whether they're rare earth species or things like lithium, which of course is vitally important for batteries in the energy sector. And then also looking at the potential for advanced treatment of non-traditional sources, brackish water sources, using various technologies. And what this plot starts to highlight is a point that will become a central point later on in this discussion, is that we have difficulties in the treatment of wastewater due to the performance of membranes, current state-of-the-art membranes. And this is highlighted in what's often been called the selectivity permeability trade-off. And that shows up here when we're looking at passage. This is now passage with numbers increasing downward, right? So this is passage of contaminants through various types of membranes here, reverse osmosis and nanofiltration membranes, as a function of water permeability. And as the water permeability goes up, the passage of these contaminants also goes up, which sets an intrinsic limit to the rate and purity with which you can purify water. Okay, so I can go on this topic for far too long, and probably for far more time than I actually have available to me. But these issues, the connection between water and energy and prospects for greater sustainability in the chemical industry have been recognized for quite some time. And we can go back to reports that were issued almost 20 years ago now that highlight exactly this. And they highlight the great potential that alternative separation technologies, especially separation technologies that rely on membranes, have to decrease the energy intensity associated with chemical separations out there in industry, right? And so in this 2005 report from Oak Ridge National Lab, for example, they highlighted high energy distillation processes with the potential for replacement with lower energy alternatives. And these, of course, have been showing up increasingly in the literature in recent years, things like olefin-paraffin separations, right? So these are alkene-alkane separations, isomer separations, recovery of dilute organics from water. Many of these processes that are performed traditionally using high energy distillation can conceivably be performed with significant energy savings if we find ways to do this using membrane technology, okay? The idea, of course, is not that we can overcome thermodynamic limits associated with separations, right? So if we think of a binary system containing a certain amount of some species A that we desire to recover at some purity Y sub A, there's a thermodynamic limit that is that dictates the amount of work that needs to be done to recover that material, if only due to the entropy of mixing, which favors the formation of a mixed state rather than the pure state. Okay, but in many cases, we're very far away from the thermodynamic minima that are associated with certain separations. And this is highlighted here in just a very simple example, looking at membrane-assisted vapor stripping to separate ethanol from water, okay? And so this brown curve here shows the energy utilization as a function of composition of a feed stream using traditional distillation and adsorption operations. The blue dotted line shows the thermodynamic minimum the minimum work that must be done to separate these two species. And this green line shows the energy that's required if this process is conducted using a membrane-assisted vapor stripping operation. So the potential to reduce the energy intensity of many chemical separations by using membranes is real and is there, but in many cases requires the development of new membranes. Okay, so more recently, I think this issue has been very nicely highlighted, for example, in the paper by Lively and Scholl about 5 years ago, that put forward some very thought-provoking numbers, right? So we know that energy consumption around the world, and certainly in the United States, a large fraction of that is devoted to chemical separations. And a large part of that reason, of course, is that we use thermal processes like distillation and other phase change operations to separate many chemical products, including hydrocarbons, and that accounts for about 80% of the energy that's devoted to chemical separations. Okay, a large fraction or a meaningful fraction, and of course it varies depending on the particular separation that's being done, whether it's dewaxing lube oils or separating chemical species which make azeotropic mixtures. But a meaningful fraction of that energy can be saved if we move from thermal separations to non-thermal separations. And in many cases, these non-thermal separations are relying on involve membrane-based processes. Okay, and they recounted, I think the title of the article was 7 Chemical Separations to Change the World. And in that article, they highlighted these 7 separations, which you'll see overlap quite substantially with the 5 separations, I think, that I highlighted from that report that was put out by Oak Ridge in 2005. Okay, so the potential for membrane-based separations to decrease the energy intensity of many industrial separations processes is real and is out there as something that we should be going after. Another area in which membranes, of course, affect our energy footprint is in electrochemical devices, right? And so whether in the form of fuel cells, hydrogen fuel cells, or methanol fuel cells, flow batteries, or static batteries, membranes play an important role in selective transport and permitting the transport of some charge-carrying species like a proton or a cation or anion, lithium cations, for example, in the case of lithium-ion batteries, while restricting the transport of some of the species that we don't want to pass through the membrane, right? This might be a fuel in a fuel cell, or electrons, for example, in a static battery. And so there are great opportunities as well here for membranes to improve the performance and reliability of a wide variety of electrochemical devices. Oftentimes that takes the form of improvements in electrochemical stability, mechanical stability as well. And of course, what we desire from these membranes is similar to what we desire in other separations. We need high mobility or conductivity, so high throughput of species through the membrane, and we need strong selectivity. There was a nice paper published about 6 years ago by Brett Helms and co-workers that caught my attention because it was a very practical solution in some sense to the problem of polysulfide crossover in lithium sulfur batteries. And what they did here is they had a computational and experimental effort that looked at a wide variety of polymers of intrinsic microporosity, so-called PIMs, and they used this particular species, PIM1, to fabricate a series of membranes that were successful in lithium sulfur battery applications by suppressing the crossover of polysulfide species, right? So separation, selective transport of species, in this case, ionic solutes. If you can do it well, you can strongly impact our energy landscape in the context of electrochemical devices. Okay, so that's a too long introduction that establishes, I hope, clearly that membranes have the potential to dramatically impact our industrial landscape, right? They can impact water, energy, food, land use. The question is, what do we need to do? We have membranes already that provide, fairly good separations in a very broad variety of instances. So what exactly is the challenge, and what do we need to do? Well, while we have solutions from membranes for a wide variety of separations, the reality is that compared to many other separation technologies, membranes are actually not yet a very mature technology. Okay, and so this point was highlighted in that 2006 report from the National Research Council, and has been echoed repeatedly over the last 20 years, I would say, including by Bill Koros and others, essentially pointing to the fact that, you know, we're not in the infancy. Membranes are not in their infancy in terms of their technological maturity, but there is a long way to go in terms of approaching the maturity of the established chemical separations methodologies that we currently use, for which we want to improve the energy efficiencies. Okay, so what's needed? Many things are needed. In many cases, what's needed are materials and manufacturing methods to produce membranes that are known to be superior to current state-of-the-art membranes. But the challenges are multifaceted, right? I mean, if you look at reverse osmosis, the efficiency of reverse osmosis desalination is within a factor of 2 in many cases, right? In many installations, certainly more modern installations, is within a factor of 2 of the thermodynamic minimum that I highlighted earlier on. And so it's really a question of knowing where to book efficiencies. And sometimes the efficiencies that one is booking through the use of membrane technologies come about more from a systems level understanding of the separations process than from improvements in very particular areas, including the materials of the membranes themselves. But for my group, our work has been very much on the material side. And in terms of material science, there are a lot of opportunities regarding the ability to make membranes which resist fouling, for example, membranes which can more robustly handle challenging contaminants. So for example, small dissolved organics in aqueous streams, for example, boronic acid, which is a perpetual problem for reverse osmosis membranes. In the context of electrochemical devices, membranes which have improved electrochemical stability, or in the context of batteries, mechanical stability while not compromising conductivity or mobility are important targets as well, right? And so there is room to improve on the current state-of-the-art membranes. For me, it's an interesting thing. If I ask my my 7-year-old daughter to draw for me what a membrane should look like, I'm certain that what she would draw is a material that had a bunch of holes running through it, in which the holes were all the same size and oriented in the same direction, and therefore providing a separation which we can sort of intuitively understand based on the size of the hole and the number density of those holes. Current state-of-the-art membranes, however, in most cases don't look anything like that, and they look quite different. And of course, they work, to a large extent they work, and they're workable, but there is significant room for improvement. Okay, and so we can begin to get a sense of what sort of improvements we should be aiming for by looking at what current state-of-the-art membranes look like in a couple of situations. And so here I've just highlighted the structure of these are membranes for microfiltration, ultrafiltration, and in some cases nanofiltration that are produced by non-solvent induced phase separation, right? And so the manufacture of these membranes is quite simple and straightforward. It involves entry of a non-solvent, in this case water, into a concentrated polymer solution or a dope that's spread as a thin film. And the entry of that non-solvent into this concentrated solution results in a precipitation of the polymer in a random tortuous structure that has an average length scale that can be used for separation. Okay, and so membranes of this type can be made in very high volumes and for very low cost, but the structure that you get as a result has a broad pore size distribution and tortuosity associated with the transport that leads to suboptimal performance. Okay, likewise, thin film composite membranes that are used for reverse osmosis desalination, and looser forms of which are also used for nanofiltration, also have strong limitations in terms of permeability and selectivity that are associated with the distribution of transport regulating features in that system. Now, the transport regulating features in thin film composite membranes are, of course, the network, the polyamide network that's formed by interfacial polymerization. Nevertheless, even at that very small length scale, the heterogeneity in the network structure gives rise to selectivity, permeability trade-offs that are also seen in reverse osmosis desalination. Okay, and this idea of a selectivity permeability trade-off also shows up in other contexts. Here, this is the famous Robeson plot for gas permeability, a very nice paper by Meni Alamelek, Benny Freeman, and others, and Robeson also highlighted the existence of the selectivity permeability trade-off in a variety of other separations. Now, that selectivity permeability trade-off, as I said, originates from the dispersity in the size and chemical nature, oftentimes, of transport regulating features in the membrane. So shouldn't we then try to build membranes of the type that my 7-year-old daughter might actually sketch if she was trying to sketch what a perfect membrane or a perfect filter might actually look like? And in fact, that's what we work on in my group, and that's what many other groups around the world are working on, and we're working on that intently because the potential to reduce energy utilization in water production, in chemical separations, and so on, is real and beckons. So what are the challenges and opportunities? Well, the first is the one that I just highlighted, overcoming the selectivity permeability trade-off, both in perm-selective and nanoporous membranes. And I've highlighted selectivity here because in many cases, it's the selectivity of the membrane that's the limiting factor in terms of its energy footprint, and not the permeability. Okay, this is true in reverse osmosis. It's true in organic solvent nanofiltration. It's true in a broad variety of membrane processes. Sharpening the cutoff characteristics and decreasing the tortuosity in porous membranes. So these are two challenges that speak directly to improving the selectivity and potentially surmounting the selectivity permeability trade-off. Most importantly, precise tuning of pore dimensions and solute interactions, right? So can we get closer to the picture of an ideal membrane that a 7-year-old child might draw if he or she knew nothing really about how membranes might actually be manufactured in the real world. Fouling, especially in the context of reverse osmosis membranes, is a large target. That's an area in which we can net significant gains. And of course, for everything that we do, for any interesting membrane or any interesting nanostructured materials or membranes that we come up with, we need to ensure that we can have scalable fabrication of these membranes that offer improved performance. Okay, and so we're talking about the ability to make thousands of square meters of material readily with a low density of defects to be able to begin to match the current capacity that we have in in spiral wound membrane modules or in capillary based systems. Okay, so we need scalable fabrication of membranes, and here I'm saying of self-assembled membranes that can offer improved performance. There are a lot of interesting areas that we can address if we were able to make membranes of this type. I'm going to run through this quickly. I've highlighted in red some of the ones that my lab is particularly interested in. For example, improved salt rejection for low pressure nanofiltration treatment of brackish waters, so surface waters, organic solvent nanofiltration below 200 Daltons, breathable materials for chemical warfare agent protection. Again, you need here molecular weight cutoffs in the region of about 200 Daltons, if not smaller. There are interesting possibilities regarding the prevention of thermal runaway in electrochemical systems, and several others. So these are 4 that my lab is particularly interested in. There are others that are listed here that represent the effort of other groups. And this list, of course, continues on and on and on if you get into the details of how membranes can actually affect energy footprints in industrial operations. But let's get into the meat of it. So what is our charge? So I'm not a systems engineer. I'm not an environmental engineer. I'm a material scientist more than anything else. And so the charge for me and the charge for my group over many years has been this one: to create highly regular structures with transport limiting dimensions in a 1 nanometer range that can be tailored precisely and which can be fabricated in a scalable manner. And so that challenge, if one is able to address it, is the key to starting to unlock the potential of nanostructured membranes to address pressing needs in water purification, particularly nanofiltration, and I would argue also chemical separations, especially in organic solvent nanofiltration. When I was at Yale, I oftentimes joke that I was the oldest student or oldest member of Meni's group, right? say for Many himself, I enjoyed collaboration with Many over many years, and we wrote a review paper back in 2016 that highlighted materials for next generation water purification membranes. And as you can see here, some of the concepts that were presented there and that are actively being worked on by my group and his group and other groups around the world entail precise definition of the transport regulating features that are used to conduct the separation in the membrane, right? So this can take the form, for example, of self-assembled structures in block copolymers, which typically are giving you separation on 5 to 50 nanometer length scales. Graphene-based frameworks, covalent organic frameworks, and metal organic frameworks are also included in that. Discrete structures like carbon nanotubes or aquaporins, or for us, what we've been heavily focused on, the use of polymerizable surfactants or the assembly of small molecule mesophases, where small molecule here is now about 1 kilodalton, that presents transport regulating features that are on the length scale of about 1 nanometer. Okay, so this has been sort of a guiding idea for the work in my group. Can we take self-assembling systems like this, and can we retain their structures over large length scales and fabricate actual practical membranes that can start to address some of the pressing challenges that I highlighted? And because I'm low on time, I won't take you through a detailed review of literature in this area, but there has been intense effort, I would argue, over several decades to make membranes using self-assembled materials, taking the form of efforts with block copolymers, for example, liquid crystal mesophases. So there's been very good work here by the Cato group. Shenning in recent years has been doing some very creative work regarding liquid crystal-based membranes. Doug Jin for well over 20 years, right? So he, I think, started sort of the revolution regarding the use of these dendron-shaped molecules to create self-assembled phases that can be used as membranes. And there's also a lot of effort involving, in some cases, more conventional membranes, where we're taking advantage, for example, of simply higher interfacial area in conventional interfacially polymerized thin film composite membranes, or the use of maybe non-traditional networks here based on cyclodextrin, or the incorporation of some sort of metal organic frameworks into interfacially polymerized systems. There's intense effort on the use of self-assembled membranes and alternate interfacial polymerization approaches to create improved membranes. But what is it exactly that my group is doing? Okay, so we started first in this area, or one of our earlier efforts in this area was a collaboration with Many Elementics group and Doug Jin at Colorado, involving these wedge-shaped dendrons, these gallic acid derivatives that Doug first published on over 20 years ago. And this is an intriguing class of molecules because these wedges come together to form disks. These disks stack into columns, and the columns pack hexagonally into a hexagonal mesophase. And they're intriguing because at the center of each of these columns, in principle, is a roughly 1 nanometer diameter pore. And we approached Doug with an idea. My group had been very active in magnetic field directed self-assembly of block copolymers. And we thought, rightly, that we could use magnetic fields to control the orientation of these columns as a way to optimize the transport properties of the resulting materials. And truth and in fact, we were able to do this. So this is a transmission electron microscope image looking down the axis of those columnar channels and perpendicular to the axis of those columnar channels. And these are systems that were produced by orienting the sample using a large magnetic field, in this case, a 6 Tesla field, right? So this is a highly regular structure consisting of columns of these dendron-shaped molecules that have come together as disks. And at the center of each of those columns is a 1 nanometer pore that offers a potential for nanofiltration. We showed also that you can control the alignment of those columns by using surface confinement methods. And if you look in the cross-section by TEM of those thin films, you can see that you have those columnar structures continuous from the top to the bottom of the thin film. And this is in a film which is about 350 nanometers. And so the potential, right, one gets excited thinking that, okay, potentially this could be a workable membrane. And potentially it could be. But if I've learned anything over the last 5 to 7 years of working with these materials, is that there's a huge gulf, there's a huge distance that needs to be traveled between, getting interesting structures, 2 by 2 microns on an AFM image or an electron micrograph, and an actual workable membrane. So, the challenges associated with bridging that gulf are non-trivial. But I digress. The interesting thing about those membranes, of course, is that those columns, in fact, do have 1 nanometer pores at the center of each column, but those pores are not true physical voids. They're filled by a dense cloud of sodium counterions, and the carboxylic acid head groups that are poking into that pore are not necessarily aligned. They're not necessarily registered as you go throughout the height of that pore. And so we came up with the idea that we can create actual true physical voids in these systems by using molecular templates. So we could take a molecule like this propeller-shaped tribasic species and use it to guide or template the self-assembly of that gallic acid derivative, here shown as the acid form rather than the sodium carboxylate form of the molecule. We could form columnar mesophases, cross-link them, and then wash out that molecular template to provide a true physical void in the sample. And in fact, this works quite nicely. So we did this, and we looked at the behavior or the properties of the system just in simple absorption measurements, right? So I hinted at the difficulty of making true membranes that one can test in the characteristic fashion, right, by pressure-driven flow. So what we did in this case is just test these membranes by absorptive uptake of molecular dyes. And what you can see here is very good selectivity based on size and charge in these membranes. So for example, here we have an aqueous solution that contained rhodamine 6G. It's a red dye, it absorbs in the blue. And methylene blue, it's a blue dye, it absorbs in the red. The combination is purple. After we introduce our polymer containing these aligned nanopores, the blue dye goes into the polymer while the red dye stays out. And the reason is that there's a roughly 0.5 nanometer difference in the effective van der Waals diameter, if you will, of rhodamine G versus methylene blue. And the same thing is seen here with basic yellow versus an Alcyon blue dye, which in fact in this case is much bigger. And then finally, we look at the case of, say, methyl orange, which is absorbing down here sort of in the blue-green, and methyl blue. The methyl blue or the methylene blue goes into the polymer and the methyl orange stays out. In this case, methyl orange is a smaller dye than methylene blue, but the methyl orange stays out because it's a negatively charged species, and the pore walls that are produced in these membranes are left with a negative charge on them after the processing. So we can get very, very highly selective membranes based on size and charge, and this was tested just in absorption, right, not in pressure-driven flow. So aligned nanopores are good, and essentially what we chased after initially was the creation of membranes in the way that my 7-year-old daughter might envision them: a thin film with lots of holes in the film, with the holes all the same size and aligned in the same direction. And aligned nanopores are good, but if you can circumvent the need for alignment, that would be even better, I would argue. And so what we've been working on in recent years is a system that involves filtration, that involves selective transport, not by flow through a cylindrical pore, as we've historically done, or by flow through a lamellar or sheet-like slit, which also requires alignment. And it's not by flow through a bicontinuous cubic morphology, for example, as you can find with the gyroid systems, where you don't need alignment, but where the pore stability of the phase makes it difficult to work with. What we've been looking at is selective transport by flow around cylindrical objects that have been polymerized in a water continuous medium. Okay, so there was a bit of serendipity involved in the discovery of these materials. These are interesting materials because this mesophase, the so-called direct hexagonal lyotropic mesophase, is readily accessible over a broad variety of molecular species. Selective transport around these cylindrical objects requires no alignment of the material, and so the processing implications are attractive. You don't need to have a separate process step for the alignment of the transport regulating features. And the idea is that then the transport regulating features are formed by the separation between the exterior surfaces of nearest neighbor cylinders. Okay, and so the mesophase that we used was one that was formed by this polymerizable cationic surfactant called MEETDAB. And of course, if I was offering this project to, a bright-eyed graduate student, they would probably tell me, Professor Osuji, this is interesting, but I think this won't work because if you polymerize these cylinders, what's to keep them from all floating apart in excess water once you're trying to use the system as a membrane? And of course, and this was the serendipitous part, the mechanical integrity, the coherence of this material is in fact guaranteed by two things. One, there are topological interactions, if you will, across the material because of the presence of defects, right? And so in the same way as an onion, in some sense, is held together by interlocking layers, these cylinders are held together topologically, and they're interconnected physically in some way. Secondly, there's a finite density of molecular crosslinks that exist between the polymerized cylinders. And what we did, of course, was to augment that by the deliberate addition of, in this case, oligoethylene glycol dimethacrylate, which anchors itself inside of the cylinders and bridges the aqueous phase to make sure that there's good mechanical integrity in the system. So our advance here really was the demonstration that these hexagonally packed mesophases could be used to create materials suitable for nanofiltration, and the identification of compositions of matter that permitted rigorous retention of the structure of that mesophase throughout the processing associated with the formation of a membrane. And so what I'm showing here on the right-hand side is X-ray scattering data looking at the structure of that gel. So the system as it forms first with water present is a gel. After it gets polymerized by exposure to UV light, you can see the structure is unchanged. And then even after swelling with water, I think this was a 24-hour exposure in excess water, there is only the tiniest bit of dilation of the sample. So that tells you that really and truly you have a mechanically robust material in which the dimensions are well preserved from the gel all the way through to the water-swollen polymer. We can see this by electron microscopy investigation. So this is TM images looking down and perpendicular to the long axis of those cylinders. And the repeat distances here, the separations between the cylinders are on the order of a few nanometers. You can see this also by AFM imaging. And here you can see the topological defects that I alluded to that are responsible for some of the mechanical integrity of this membrane. The nice thing for us about these membranes and why we think this is potentially a nice addition to the portfolio of materials technologies that exist in the membrane space is that they truly are highly ordered regular structures about which we know a great deal, courtesy of the fact that they're regular and ordered. Okay, so the two things that we control, of course, are the size of the molecule that we use in making this mesophase and the volume fraction of the molecule that is required to form a mesophase of a certain symmetry. Based on those two things, which reflect themselves in structure characterization by something called the D-spacing here, and the volume fraction of the surfactant in the mesophase, which we use to define this parameter Z, all the relevant dimensions that pertain to transport regulation become accessible to us. And in this case, if we have transport perpendicular to the cylinders, then the transport regulating feature is defined by this dimension S sub x. If we have transport into the plane of the screen, then the transport regulating features are defined, for example, by this pink shaded area, and the largest circular cross-section that can pass unimpeded parallel to the cylinders is provided by this dimension 2 delta. Okay, and the nice thing about this, of course, as well, is that we know also all of the relevant physical chemistry that might be important for controlling the interactions of that membrane with solutes as they pass through the material. So we know the specific surface area, surface charge density, ionic strength, et cetera, et cetera. Okay, so I'm almost out of time. Let me run through quickly some of the results that we've been able to get with these materials. So our first foray into the membrane space involved the creation of membranes by physical pressing. So we took these highly ordered gels and we pressed them down to thicknesses of about 20 or 30 microns. And we formed composite membranes by supporting these gels on porous polyacrylonitrile support layers. And the membranes that we created in this fashion, we tested in dead-end filtration with a variety of cationic and neutral dyes, and saw that we had interesting cutoff behavior at about 1 nanometer. And of course, that cutoff behavior was a lot stronger for cationic solutes than it was for neutral solutes, because the surface of those cylindrical objects is positively charged due to the presence of that quaternary ammonium species. We had water permeabilities on the order of 10 LMH per bar, and this is thickness normalized. And we were working at fairly low applied pressures of about 30 to 80 PSI, right? Reverse osmosis is, typically at something like 800 PSI, so a decent order of magnitude higher pressure. And these were interesting membranes as well because they were able to suppress bacterial growth due to the presence of that quaternary ammonium species. And so that has positive implications for fouling and control of fouling. What we've been able to show more recently, this is a paper that just showed up, I think, last week in ACS Nano, and this took quite some doing, but what we've been able to do is to transition similar ideas from 20 micron thick films produced by mechanical pressing to films that are now on the order of 200 nanometers in thickness that are produced using a solution processing method. And the difference is a non-trivial one. This is a factor of 100 change in the thickness of the selective layer, which for a given pressure drop corresponds to a factor of 100 in the flux, in the volume of water, for example, that might be produced by this membrane. And so all of the work, all of the magic was in finding materials that we could, with which we could formulate a mesophase using a non-volatile medium that would allow us to do solution processing. And so this was the work of a postdoc, Yiqiu Zhang, in my group. And his results show that, okay, you can create now these thin films, selective layers that have thicknesses very similar to the selective layer thickness in reverse osmosis and commercial nanofiltration membranes on the order of, say, 200 or 100 nanometers. And we can control the thickness of that selective layer very easily, simply by the concentration of the solution that we use to spin coat and fabricate these membranes. The results from transport characterization are attractive and compelling. So this is looking at rejection for these membranes when confronted with polyethylene oxide solutes of different sizes. And this is done for membranes produced on PAN support layers versus membranes produced on PVDF support layers. And the molecular weight cutoff here corresponds, or the size cutoff corresponds to solutes on the order of 1 to 1.4 nanometers. Okay, if you look at rejection of molecular dyes, the molecular weight cutoff is maybe in the region of 400 Daltons. But here the transport is affected also by the fact that the dyes are charged and the solid surfaces within the nanostructured membranes are also charged. We looked at salt rejection in these materials, and we can see data here that is quite typical for nanofiltration membranes, quite strong rejection of divalent salt species relative to monovalent species, and the characteristic fall off in that rejection that you expect as you increase the ionic strength of your feed stream due to electrostatic screening. What for us was very attractive, though, was the performance of these membranes when considered against commercial nanofiltration membranes. And so we did low pressure nanofiltration testing, and we benchmarked the performance of our membranes here, shown in red, for divalent and monovalent salts, open and closed symbols respectively. And we benchmarked those membranes against a series of commercial nanofiltration membranes. And we found performance that is intermediate between what I would describe as two class-leading commercial nanofiltration membranes, namely Dow NF90 and NF270, which is a slightly looser thin film composite nanofiltration membrane. So they have attractive transport properties that rival and in some cases exceed commercial membranes, and they can be fabricated using scalable solution-based techniques. We've extended this recently to look at organic solvent nanofiltration in this same series of materials. And here for us, the really compelling thing is that we can change ever so slightly the structure of the molecule that's used to make the mesophase that provides the membrane, or we can change the volume fraction of that surfactant and in so doing, change in very small increments the dimensions of the transport regulating features that are provided by that membrane. And so this is a work in progress, and that's what Yicho did. He looked at a series of different surfactants with differing chain lengths and a few differing cross-linker chemistries, and in so doing, produced membranes with a small but precise and steady variation in the expected transport regulating feature size, and looked at the resulting changes in the rejection properties of these membranes. Okay, and so I'm beginning to run out of time. I will hop forward to the relevant results and draw your attention to these molecular weight cutoff curves. So this is rejection as a function of geometric mean diameter for solutes passing through these membranes. And we see that for changes in the, chain length of the membrane, we can get quite small but steady changes in the molecular weight cutoff behavior of the solutes that are transiting through those membranes. Okay, we compared the performance of our membranes against a variety of membranes, nanofiltration membranes that have been reported in the literature recently, and we have pretty attractive rejections. This is methyl orange, is a standard molecular dye. Not necessarily the greatest probe molecule, but here it's a single point measurement that allows a faithful comparison against literature data. And we can see that here we're up in this upper space here where we have high rejection and modest, but definitely usable permeances in these membranes, right? Likewise here, this is permeance as a function of thickness. Of course, inverse thickness, in principle, this should be a straight line. In practice, it's not, and a lot of literature data falls sort of below, this is no real physical limit, but a lot of literature data falls below this line for reasons that are not quite clear to us. But for the membranes that we were working with, we were able to get quite attractive permeances for methanol at thicknesses on the order of about 200 nanometers. Okay, I'm running out of time. The last bit I have to say is, we're hard at work looking at these membranes in a broad variety of settings. They're also interesting materials for ion transport. And so I highlighted the potential for membrane technology in electrochemical devices. We've been looking at membranes made by these polymerized mesophases in the context of ion transport, and specifically in the context of hydroxide ion transport, because we're compelled by the potential to apply them in methanol fuel cells operating under basic conditions. Okay, so this is still quite preliminary work. Obviously here, stability under strong basic conditions is a strong consideration. And so we've been modifying the chemistry of this molecule, getting rid of this ester linkage and looking at an amide chemistry. And we've seen thus far that the transition to this amide chemistry has provided us with fairly good stability. Here just tested over 2 weeks at ambient temperature. We're now moving up to higher temperatures. And we have a fairly reasonable hydroxide ion conductivity, not world beating by any stretch, but certainly good enough to start to think about the potential of these materials in electrochemical devices. Okay, I'm out of time. I'll summarize here by saying the following. The main focus for us as material scientists trying to contribute to membrane technology, which has so much to contribute to the water, energy, and food nexus, is to create membranes in which we can tailor pore sizes and eventually pore chemistry precisely. And we can do that now by using this allotropic mesophase approach, by changing very carefully the size of the molecules that we use to create these membranes and the composition of the phases that we use to create the membranes as well. We've been able to see attractive transport properties in both aligned systems, as I did not talk about, but also water continuous systems. And these transport properties are encouraging, and there's certainly lots of room for improvement. I think the contribution really rests on the fact that we can now make these membranes using solution-based processing routes. And so that permits scalable fabrication. And we're looking at membranes down at a couple hundred nanometers of thickness with pore sizes that are sub 1 nanometer and variable by units of probably 0.1 or 0.2 nanometers. And so there's a lot of potential there for membranes, certainly in water purification and organic solvent nanofiltration, but we think also potentially in electrochemical devices. And there are other applications as well. Gas absorption, chemical warfare agent protection that I didn't talk about, and then electrochemical devices, as I mentioned before. So with that, I'd like to acknowledge the members of my lab who have worked in this area over many years, and also my one-time collaborator, Meni Elimelech at Yale, from whom I learned so much. It truly is humbling to try to take a beautiful nanostructured material and make a membrane out of it. There's a gulf that separates those two that is decidedly non-trivial, but we think we're starting to surmount those difficulties in some cases, and so we hope that the future in this area is bright. Thanks for your attention. I'll be happy to take any questions that you have.
Wow, thank you, Chinedum. That was a beautiful talk. I will applaud on behalf of the audience. The crowd is going wild, I'm sure. So we have several questions that were in the Q&A. First, I just want to mention that that was just a beautiful example of how soft materials engineering can really address this important problem. And I particularly found it fascinating that introducing defects plays such an important role. So we had a few questions from the audience. First, you ended by suggesting that electrochemical applications may also, these membranes may also have an influence in electrochemical applications. And so David Quabi asked, what are the prospects in electrochemical applications, for example, in flow batteries where active reactants need to be kept apart, but fast ionic conduction is needed? And then David also asked a second part, to what extent do you think electrochemical rather than mechanical, for example, pressure-driven techniques with membranes methods can play a role in desalination?
That's a great question. So I'll tackle the first part of that question first. If I'm brutally honest, which I oftentimes am, and which I think we should be when we're trying to develop real materials for real-world applications, I don't think that the electrochemical devices are the first area that, or the most attractive area necessarily for these membrane materials. I think that alkaline fuel cells are compelling, right? Because you have a much lower requirement in terms of the catalyst that you need to use to drive the process, but you have a much higher requirement in terms of the electrochemical stability and the stability of the material under strong basic conditions over time. So I'm not certain that that's actually the best area for practical application for these materials, though we are interested in understanding something fundamental about the relationship between, for example, confinement, transport, in these materials. And can you repeat the second part of the question? Sorry.
Yeah, the second part of the question was, to what extent do you think electrochemical rather than mechanical pressure-driven methods can play a role in desalination?
Yeah, that's a great question. So we have not, in my group, we've not looked at anything along those lines. So I think there's a lot of potential with electrodialysis, for example. I think that there's a lot of exciting work going on in this area as well. Some of it involving nanostructured materials. That's well beyond the scope of anything that my group has gotten into, but this is also an interesting area to look at.
It's an interesting area. I should mention you mentioned Meni Elimelech, your collaborator and colleague on this work. Meni is actually an advisory council member of the Endlinger Center. Right. So small world. So Wen Ma asked, I think, another useful question here. What is the major challenge that limits scale of fabrication of these membranes that you presented? Right. So, I think everything that we've done prior to the last 2 years was very interesting, but not hugely practical. I would argue, and I think my students would certainly argue forcefully, that for the first time we feel like we're in a position maybe to do something that could be practically relevant, because these membranes are made using a solution process. Right now we're using spin coating because it's lab scale, but the connection between a spin coating based deposition and something like blade coating or dip coating, of course it requires significant optimization, but we can get there starting from spin coating. So what are the roadblocks to scale up? I think porting the spin coating over to blade coating or dip coating certainly is one, but I think that's completely doable.
But of course, just because you've built a nice looking nanostructured membrane, or maybe even a better performing membrane, doesn't mean necessarily that you're in a position to address some of the dire challenges that I highlighted at the start. And so again, it's really about finding the particular areas where your materials can make a difference. So one of the places that we've been investigating is nanofiltration for the microelectronics industry, where the requirements for the removal of particulate matter at the 1 to 3 nanometer length scale are extremely stringent. And so it's really about finding niche areas where new materials can provide some improved function or maybe some cost savings. And no one membrane can solve all the problems. But I think that we're finally at a point where scale up is actually conceivable.
Yeah, that it's an exciting future. There are several more questions, so I'll just roll through. We probably won't be able to address them all in the interest of time, but a more technical question relating to the actual membranes. Well, I know Unal asked, what reinforcing fibers do you use in your membranes? And a related question that I had was, you showed how beautifully that defects, which we think are a bad thing, actually help reinforce the membranes in your case. So one can presumably imagine rationally introducing defects. But then there's probably a trade-off. If you have too many defects, then that compromises the membrane. If you have too few, then maybe that compromises mechanical stability. So can you comment on the potential for rationally introducing defects as well as the fibers that you use for reinforcement?
Sure. So we used standard mechanical supports, and in this case, actually, we haven't used. In some cases, there was a non-woven backing. In other cases, there wasn't. We didn't pay a great deal of attention to that. And for the most part, the mechanical support methods that we're using are similar to what you might find used for commercial thin film composite membranes, right? Either with or without a woven backing. Most often we just use, commercial PVDF or commercial PAN porous supports. In terms of defects, it's a good question. I don't know that, so those defects are defects of a nature that aid mechanical integrity. They probably have some implications, not severe, for transport regulation. For us, potentially the more interesting question, and I glossed over it because there wasn't time to get into it, is that in looking at these direct hexagonal systems where you have transport around cylindrical features, the transport regulating dimensions depend on the orientation of the cylinders. And in fact, in that last set of data that I highlighted regarding organic solvent nanofiltration, for the smallest molecules that we were working with, we had cylinders which were vertical and horizontal in the film. And so there was a broader distribution of transport regulating features produced in that one case, than was present in some other cases where we had the cylinders all parallel to the surface in a planar configuration. So I think the defects are potentially interesting, but probably more meaningful impact can be had by looking at the orientation of the cylinders.
That makes sense. And I think in the interest of time, maybe I'll just ask one last question that was asked by Kofi Christie. And this is kind of taking a step back and looking at the big picture again. Kofi asks, many of the applications for membranes in wastewater are well established and the standard materials work quite well. What, if any, opportunities for entrepreneurship exist in membrane development?
Right. That's a great point. Thank you for the question. And one of the things that I learned working with many is that you have to, we're all passionate and enthusiastic, but we need to be aware of the realities that are out there, right? And so it really is about finding the niche areas where you can make a difference. Okay, so probably it's not permeability, but maybe it's selectivity. If it's not selectivity, maybe it's in avoiding the need for significant pretreatment in a membrane process, which drives up the price. If it's not that, maybe it's in reducing fouling, which reduces the downtime that's associated with a water purification operation or something like that. So there are very few cases that I can think of for which we don't have some membrane somewhere that is capable of performing the process. But if you're careful about the particular application that you're looking for, you can find these areas where improvements to the structure, improvements to the materials, and improvements to the processing can open up opportunities to you. So we think that there are potential opportunities out there in nanofiltration, and in particular in low pressure nanofiltration, where our membranes seem to perform quite respectably against sort of class-leading state-of-the-art materials. And there's a lot still to be gained, I think, through optimization of our own methods, and we're continuing to work on that.
Thank you. Well, with that view towards the future, thank you once again, Professor Osuji, for a beautiful seminar, and that'll conclude our highlight seminar for today. Thank you.
Thank you. Rob?